Welcome to On-Ramp. On our way to MBA 643, I am Dr. Danielle Morin, and this is Module 5, Descriptive Statistics, Measures of Dispersion. We have started in the previous module to look at descriptive statistics. We have studied measures of location, and now we will look at measures of dispersion. Measures of dispersions are measures of variability which are used to describe the spread or the dispersion in my data. We will see 5 measures. We will look at the range. We'll look at the interquartile range. We'll look at the variance, the standard deviation, and the coefficient of variation. So let us start by defining this. We want to describe the variability or the spread of a set of data. So by using variability with measures of central tendency that we saw in the previous module, we have a more complete description of our data set. So dispersion explains how far the data is spread apart or disassociated from the mean. It's all about the distance from the mean. The first measure, and the easiest one, is the range. We have talked about that in previous module. So the range is the difference between the largest and the smallest values in the data set. This difference is always positive. It's useful because it's so simple to compute. It's important to know the range of my observations, but, well, there are a few disadvantages. Well, it only considers 2 points in my data, the smallest and the largest. So it doesn't look at what happened in between. And of course, because of its definition, it's influenced by extreme value. It's based on the largest value. So if the largest value happens to be an extreme value, it will change the range very much. It has no reference point. We cannot tell what is a small range or a big range. There's no reference point. And its limited use is by itself. There are no other tests. There's nothing associated with this. If I have a very small sample, 13671, then I identify the maximum, which is 7. The minimum is 1. The range is 7 minus 1, 6. The interquartile range is the second measure that we will study. The interquartile range is the distance between the third and the first quartile. So I take it as Q3 minus Q1. In the previous module, we saw how to calculate Q1, first quartile, and Q3, third quartile. In the distribution of data, I have 25% of my data here between the first and the second quartile. We remember the second quartile corresponds to the median. We have another 25% here, which is the distance between the second and third quartile. Bigger than the third quartile, 25%, and under the first quartile, 25%. The interquartile range will be that distance. So it contains the value in the interval between the first and the third quartile. And it accounts for 50% of the observation in an ordered array. Is the interquartile range influenced by extreme? It's very unlikely, because we see that it's only the middle value. The extreme value will be on either side, either very small or very big. So this measure is user-friendly because it is not influenced by extreme value. So let us calculate the interquartile range of this data set that we saw in the previous module. We already established that Q1 is 24, Q3 is 42.5, and the interquartile range will be the difference between 42.5 and 24. We subtract and we find 18.5. how do we interpret that? It means the age of the middle 50% of people who went to see the movie are between the age of 24 and 42.5. It means also there were about 25% of people less than 24 and 25 above 42.5 years of age. This second measure is easy to use as long as we have our quartiles. The third measure is the variance. There are two formulas to calculate the variance, one for the population and one for the sample. Notice here I have the Greek letter sigma. It means it's the population. So the population variance is the sum of square of the deviations of the observation from the mean. The mean is mu, population mean, divided by the number of observations. So if I calculate this, the units that I will have at the end will be units square. If I measure kilometer, the variation for kilometer will be in kilometer square. It makes interpretation quite difficult to do, because how can we work with kilometer square or dollar square or children square? We cannot work with this. So this unit, this measure would be much better if we could take the square root. And this is what we will do when we look at the following, the next measures. That's my population variance, and my sample variance, the only difference here, I divide by n minus 1. Now the reason for dividing by n minus 1 instead of n is beyond the scope of this program, but let us say that this estimator, S square, is quite good at estimating the population variance. But once again, the units at the end will be unit squared. So I have the same problem as we had with the population variance. So let us take this example. What is this variance? What is the variance of this data set? I have a sample of size 20. We either use a calculator or we use Excel. Some people like to do it manually, step by step, but honestly, it's a waste of time. So if you have a calculator, there are functions in the calculator as you can get directly the variance. And of course, Excel, it's only one click away. Variance.s, and this S stands for the sample. If I want the population, I would choose variance.p for population. So variance.s will end the range of my observation from A1 to A20, and it will give me 160.3658 year square. See, as we said before, the original data was year, but the variance is in year square. It's quite hard to interpret. What does it mean, 160 year square? It's not user-friendly. We cannot do much with this. So again, if we want to do it the long way, if one would like to use it with a calculator, but step by step, instead of just asking for the function on the calculator, we can use this shortcut formula. I need two information. I need the sum of square, the sum of those observation squares. So 24 square plus 35 square plus 17 square. If I have this, and if I have also the sum of all these observations, I can use this shortcut formula. So of course, I need this sum of all those 8, so if I add them up, I'll find 649. If I square each observation and add them up, I find 24107. And when I substitute in the equation, I find the same answer, 160.36.58. Although I recommend that you learn how to use your calculator. Maybe Excel will not always be available, but your calculator, small, user-friendly, should always be. Study your calculator and see where the function variance will be. Once you know that, it's only entering the data and a click and you get your number. So let's be saving time and not having to do this the long way, especially in an exam setting. Now, if I take the square root of the variance that I had in the previous slide, I get what we have, the standard deviation. If I take the square root of the unit square, it's the original unit. So the standard deviation, this new measure, is simply the square root of what I had before. This is in the units, the original units of my data. The function is standard deviation dot p or standard deviation dot s for sample. And this sample standard deviation S, as we said, is a quite good estimator of the population standard deviation sigma. Variance was sigma square, standard deviation is sigma. Variance was S square, the sample standard deviation is S. So that makes it very easy to obtain. It's simply the square root. So in our example here, I would like to find the standard deviation. So it's simply the square root of my variance. Now it's 12.6636 years. So we already know the mean of this sample, but now we know also the standard deviation. And this is another measure that is given to us when we use directly the function descriptive statistics in Excel. In fact, in all programs. But what is the use of standard deviation? The standard deviation is often used in finance, and it is an indication of financial risk. For example, I have the first financial security A, and the annualized rate of return is 15%, but here the standard deviation is 3%. That means there is a certain variation. It will not be 15% all the time, but it will be a little bit more, a little bit less. But if financial security B also has the same annualized rate of return, but a bigger standard deviation, so that means the peak will be bigger. It could go higher and it could go much lower. Just take 15% plus 1 standard deviation, now we are at 22%. Nice return, but it could be under 15% minus 7%. It could be down to 8%. So we say those who choose security with large variation are not risk averse. Those who take smaller variation here, they are the type who are more risk averse. Of course, if you have larger deviation, you stand to make more, but you stand to lose more also. It depends how we are with our resistance to risk. Standard deviation is also used in quality control charts, because a process is in control if it is within a certain number of standard deviation. So if it exceeds a certain number of standard deviation, we stop the process because it's out of control. There are many more errors that we are willing to accept. Again, standard deviation is very useful in this field. We are having now another measure of variation. They all look at the same thing. It's the spread. So the more the data is spread out, I think we understand that the range will be bigger, the variance will be bigger, and the standard deviation will also be bigger. If the data is more concentrated, they're all around the mean, so we'll say that we have a smaller range, smaller variance, and smaller standard deviation. What happens if all the values are the same? 5, 5, 5, 5, 5. So what happens with the range and the standard deviation and the variation? It would be 0. Of course, if all the data is 5, 5, 5, the maximum is 5, minimum is 5, 5 minus 5 is 0. So there will be no variation. So all those measures would be 0. Keep in mind that all the measures that we have seen can never be negative. If the values are all the same, it's 0. Whenever there is a movement in the data, there will be a positive standard deviation, a positive variance, and a positive range. But all of them are sensitive to extreme value. The range, it's obvious, but also the variance, which calculate the distance between the observation and the mean. So if that observation is an extreme value, it's going to inflate all my results, and I will have a much bigger variance and much bigger standard deviation. A very interesting concept that is introduced is another measure, which is the coefficient of variation. So it is a measure of relative variation, which is expressed in percentage, and it shows the variation relative to the mean. So the answer is a percentage, no units, no unit square. In fact, what it does, it compares the standard deviation relative to the mean. So that helps me, because we can have the same variation. It costs $10 plus or minus $2, or it could cost $1,000 plus or minus $2. So that relative to the mean, the first option has much more variation. If from 8 to 12, then for 998 to 1,002. This has to be kept in mind. It allows me to calculate, to compare household income in 2 cities, or the employees that are absent from work in different plants. It depends on the variability. So the standard deviation related to the mean. Let us see an application. Let us consider 3 stocks, and we want to know which one has the largest variation relative to its price. Stock A. The average price last year was $50 and the standard deviation of 5. Stock B. The average price last year was $100 and the standard deviation $5. Stock C. The average price last year was $8 and standard deviation $2. So which stock has the largest variation relative to its price? If I only look at standard deviation 5, 5, and 2, this ones seem to have the smallest. Stock C seem to have the smallest variation. But is that the case? Let's calculate. The coefficient of variation for the first one, S, standard deviation 5, divided by the mean 50, according to the formula, times 100%, it's 10%. Is it big or is it small? We cannot say. It is used to compare. Next one, stock B. Average price last year was $100. Standard deviation 5. Coefficient of variation will be 5 over 100, which times 100%, so it gives me 5%. Stock C. Coefficient of variation would be again my standard deviation 2 divided by 8 times 100% is 25%. So which one has the largest variation relative to its price? It's stock C. Although the standard deviation alone was smaller than the other, but when we compare it to the mean, it's bigger. So the coefficient of variation gives me another measure that allows me to compare my variations between my data. Another measure of dispersion, which is used mainly in time series, it's called the MAD, the mean absolute deviation. When we have introduced the variance and saw that I have to take each observation minus the mean and square it and then add them up, one could have thought, why don't I take only the absolute value instead? So I could take each observation with the mean of 32.45 minus the mean. 24 minus 32.45, 35 minus 32.45, and so on. I take all those differences in absolute value. Absolute value means whatever, whether it's negative or positive, it will give me a positive number. Like the first one, 24 minus 32.5, it's a negative number, but with absolute value, it's positive. If I did not have the absolute value and add up all those differences, I'll find 0. But now I take the absolute value. So it's taking its absolute value, and I add them up, and I will find the MAD 10.294. This is used, as we said, mainly in time series. This will be to assess the accuracy of a prediction. We are not in time series yet, but we should know what is this measure. So if I use Excel, it will be average AVDEV, so the average deviation from A1 to A20. So often there are some rules that are just with experience that we come. Rule of thumb. We say that often the standard deviation is 25% larger than the mean absolute deviation. Let's see in our case if it makes sense. The standard deviation that we have was 12.6636, we just calculated before. And if I take the MAD, multiply by this 25%, 1.25, my MAD, it gives me 12.8688. So my 1.25 of the MAD is not too far from the standard deviation. So this rule of thumb, it's an approximation, and the key word is often. Often. It doesn't mean all the time, but often it will be something that is close to the standard deviation. So we have seen several measures of dispersion in this module, and they will be widely used in everything we will do in MBA 643. Now it's time to take a review test. So I hope that you have understood the different concepts. Please learn how to use Excel to perform those calculations, and also learn how to use your own calculator. A financial calculator will be very good. So we'll see you at the next module. Enjoy!